shall we start? Hi, everybody. A few things for the exam. I mean, it's going to be same time here, right? So I guess we can simply fit into this lecture hall based on the numbers. So the exam would be here, same time, after the reading week, right? And then I'm going to post you a bunch of sample questions that in case you want to practice. And then you can use them, but the TA would solve them on Monday, right? Not the next Monday, which is reading week, the Monday after, so one day before your exam. So you could essentially just study by then, and then you can just ask your questions on Monday. So that would be more effective, I guess. And the exam is going to be easy. I mean, it's going to be in the range, the order that you have your assignments, so you don't need to really worry about that. As long as you're fine with the assignments, you're going to be fine there. You do know that there are going to be no programming questions. So you have your own project and assignments, no programming there. It's just going to be questions, right? Anything that you can answer by hand. This is regarding the exam. For the assignment 3, I am going to upload it this week, but I do consider like reading week is skip, right? I just uploaded earlier so you have access in case you want to start. So like reading week, I do not count it. So the week after is going to be your deadline, and then you have 2 weeks from then, right? So excluded. Reading week is excluded just to give you the chance, I mean, in case you want to plan, given that probably you have other exams and other courses, so you have more time. But of course, reading week is excluded. So that's a few things about logistics, and then let's start with today's lecture. So today we're finally going to get into the support vector machine. So we finally get out of the linear models, and we start with the first thing, which is going to do the nonlinear sort of learning. So this is the idea of support vector machine, and in order to understand that, the first thing we need to do is to just try to solve the problem of SVC, support vector classifier. We tried to formulate it last lecture. So what was the idea in support vector classifier? What did we want to do? So we wanted to do the classification. Still we are using a linear model, meaning that whatever space we are just going to draw a line, right? And we are always thinking of a binary classification. So we draw a line, a hyperplane in that space that we are working, and then anything one side is going to be labeled, for instance, +1. Anything the other side is going to be labeled -1, right? This is the linear model, so we talked about this quite some time. And then we have this kind of linear model in the one-dimensional space. So our data is simply a bunch of points. And these points, I mean, each of them is labeled differently, right? So this was the cat or dog example, right? In the cat or dog example, green guy is the cat, red guy is the dog. These are weights of them. And we wanted to just find a model which we just threshold. I mean, we put a threshold. One side, anyone heavier than that threshold is a dog. Anyone lighter than that is a cat, right? So in that example, we said that if we want to do it, we should put the threshold line somewhere in between, right? Exactly in between of the two following points. And the reason was that if we take any side, then we are just increasing the chance of getting error afterwards when we get a new point, right? So this was the whole idea of support vector classifier. So we wanted to somehow classify with maximum margin to the boundary points, right? So we put the threshold, the boundary, somewhere that the points very close to it are in the maximal distance from that threshold, right? And we tried to just extend it to the higher dimension case. So we thought of a more general case where we have a higher dimension. We played around a bit with the math. And finally, we ended up with such a formulation. So we have one particular point, or a bunch of points maybe, those n star points. They are the points which are very close to the bound, right? So the boundary that we sketch there are a bunch of points which are very close to that, correct? And there are a bunch of points which are far away from that. So we don't care about those guys who are far away, as long as they are classified properly. The only thing we care are the points that are very close to the bound, right? And then we try to somehow put the line in a way that the distance of these points from this line is somehow maximized, right? And then we just went through a bit of math, and finally we ended up with this problem, right? So this 1 over norm of the weight vector was the distance somehow, and then we wanted to just maximize this guy, given that we have that constraint. So what was the constraint for? Why I need the label Vn, Vn is the label times the linear transform of every single point to be always more than or equal by 1. What was the reason? Great. So we wanted to ensure that we are not having any error in our data set, right? So we could look at it in this form. So instead of maximizing the norm, we can just 1 over the norm, we can simply maximize it, maximize the norm itself, right? So we just maximize the norm. We try to just find the maximal margin. So, minimize the norm, which is essentially same thing as doing the maximum margin, subject to, again, this constraint. So just once again, keep it in mind. This guy, so this guy, the first box, is the kind of maximization of margin. So when we are minimizing that weight, we are essentially trying to make maximum margin. Simply speaking, we try to draw the line such that any point close to it is somehow in the maximal distance, somewhere exactly in between. And the second box, the constraint we have in this optimization, is simply to guarantee every single point inside the data set is getting classified correctly. Okay? So everybody's happy with this? Everybody recalls that? Great. So if you recall this, now the thing that we are going to do today, we are going to understand what is support vector machine. So what we did here in the other session, it was support vector classifier. It's still a linear classifier, but we want to just extend it to nonlinear cases as well, which is going to be support vector machine. And to do that, we are going through a couple of steps. The first step is to just solve that problem, the problem that I showed you in the previous slide, the one which we derived last lecture. We try to solve it. This is a constraint optimization problem. You had the other tutorial on the Lagrange multiplier. We basically want to do that, but I'm going to recap it quickly. And then we use Lagrange multiplier. We solve it. Once we solve it, we're going to see some good behavior, some interesting property. And that is that we see that SVC is essentially doing what we call a sort of cross-validation. So you just need to know cross-validation, the cross-correlation between the points in order to be able to do support vector classification. And given this idea, then we try to just build the new idea, the idea of just going to the higher dimensions in order to get rid of the issue of nonlinearity. So we're going to see it. We're going to see that idea properly, which defines the support vector machine. And then we also learn the so-called kernel trick, which is going to help us solve the problem of SVM very efficiently. Okay? So that's the story for today. And then let's start with first solving the problem of SVC. So we want to do support vector classification. And what we want to do is essentially to solve this optimization problem. Okay? So I want to just solve this optimization problem. Here in this optimization problem, I have one objective. What is the objective here? Can you tell me? Objective function? Minimize what? What is that function that I want to minimize? Norm function, right? That is what we call it objective. What is the constraint? The inequality, right? So how many of those constraints do I have? I don't have one. I mean, that should happen for every n, right? So I have capital N different constraints. If I have 10 points inside my data set, I essentially have 10 different constraints, right? So my optimization is going to look like minimize it's going to look like minimize norm of W squared. So this is the objective, subject to, first thing is that V1, label of the first point, times W transpose X1. So this is the first data point. This is the weight vector that I have. This is the label, this guy being more than or equal by 1. V2 times W transpose times X2 should be again more than 1, right? And so on till the last guy. So Vn times W transpose Xn should be more than 1, right? So I have n different constraints here, one objective, and I want to solve this problem. This is what we call it constraint optimization, right? Now, what is happening here? What does the constraint do to us? The constraint is going to just make the region of feasible points limited, right? So we cannot solve it as it is an unconstrained problem. Meaning that if I want to solve this problem without thinking of the constraint, so if I don't look at that subject to, what would be the solution? What is the minimum norm? It's 0, right? So the vector of all zeros is simply the solution to the unconstrained problem, right? So if I don't have the constraint and I just want to minimize the norm, I need to put that vector to be 0, right? But can I use this solution? Can I put this solution as the final solution? Obviously not, right? Why? Because it's not satisfying the constraint, so it is not a feasible point, right? The feasible point is that the one which is satisfying all the points in the constraint, right? All the constraint that I do have. So meaning that if I take this 0 solution and put it inside this constraint for any point, 0 times x is going to be 0, times the label is going to be 0. So for every single n that I have, this expression with solution 0 is going to be 0, which is not more than 1, right? And because of that, this is not a feasible point, so I cannot think about this. So I do know the solution of the unconstrained problem, but once the constraints come, then I am limited in the choice of the weight. Now, among those guys, I need to just find the one which is minimizing, right? So everybody's clear, right? Okay, great. So you have this idea. Before I start with the optimization problem, let's just recap a few things, again, on the curve. So this is the one which we used when we did like the derivation of the support vector classifier, right? And then in this one, we said like this is going, the yellow line is going to be the boundary, right? And now there are a bunch of points. These points are the ones which are very close to the boundary, right? What did we call them? What did we call these guys? These, I mean, the green and red guy here. What is it? Support vectors, great. So these are the support vectors, right? These are the guys who are very close to your bound, right? And for them, you remember that when we were doing all the derivations, we set that expression, Vn times linear transform, to be exactly 1, right? So for the support vectors, you keep it in mind. For the support vectors, that constraint that we have is happening with exact equality, right? These are the points which are very close to your boundary, right? Now, any point which is more far away from the boundary than those support vectors, for them, that constraint is happening with what? With a strict inequality, so it cannot be 1, because we do know that it is more far away from the boundary. You remember it? So if you don't exactly remember what we did last time, keep this in mind because we're going to use this, okay? So these guys are the guys which we call them support vectors. For support vectors, those constraints that we have are happening with exact equality because they are the guys which are closest guy to the border. And for any other point, this constraint is happening with a strict inequality, right? This is important. Everybody's happy? Yeah. Okay, so if you got this, then let's get back to the problem. So we have a constraint optimization problem. We can think of a more general problem in this form. So this problem is like you want to minimize an objective function subjective condition to a bunch of inequality constraints, okay? So let's think of the problem first in general. If I want to do that, anyone has a clue how I can solve this problem? First of all, if I don't have constraints, how can I solve that problem? Any algorithm you can think of? Say I don't have the constraints, how can I solve the problem? Any algorithm that does the minimization for me? Gradient descent, right? Or set the gradient to 0. It's the same thing, right? Either use gradient descent or compute the gradient, set it to 0. If the problem is convex, you just find the solution. If not, you might just search for the solution among the ones you find, right? So you can do it when it's unconstrained. Now, when it's constrained, any clue? What can I do? I can define something that we call it Lagrange dual function. Now, before I go on, in the SVC problem, that f, that objective function, is simply my norm. That g, that constraint, is 1 minus that term, because I am putting the constraint to be one function less than or equal by 0, right? So in SVC, in support vector classifier, my constraint looks like this. Is Vn times W transpose Xn being more than or equal by 1, right? I can just play around with this inequality. I write it down 1 minus Vn W transpose Xn being smaller than or equal by 1, right? And then I just take this guy as the Gn, correct? So I just make it the Sonnet form and then use it, okay? Once I solve this problem, the above problem, then I just put that Gn inside the solution, put the objective to be the norm of weight, and then I'm going to get my solution for SVC. Correct? Okay. Now, in order to define the dual Lagrange objective function, what you can do, some of you might know it, but if you don't know it, no worries. Just take a look at here to just get the idea. So what is the idea? I have n different constraints, right? So here, just look at the board. I have constraint number 1, constraint number 2, till constraint number n, correct? So for every single of them, I am considering one dual variable, lambda. Lambda 1, lambda 2, till lambda n, okay? These are my dual variables. And now, these variables are like sort of auxiliary variables, new variables I just defined, okay? And I make a dual function, a function out of the problem that I have, in this form. This is what I call it the Lagrange dual objective function, or simply dual Lagrangian. So what is the dual Lagrangian doing? It's getting my own objective f, so this is the objective that I want to minimize, and then it adds up every single constraint that I do have, all of them, with some coefficient, which is exactly the dual variable, that auxiliary variable. It multiplies it with that and sum it up. Okay? So this is the Lagrange dual objective. And now this dual objective is constrained to have all of those dual variables, lambdas, non-negative. So they are either 0 or positive. Clear? Cool? Now, why do I define such a function? Why do I need such a function? So this function has one specific property. What is the property? Let's look at this problem, this function. First thing that I do, I think of feasible points. And what do I mean by feasible points? I mean that I have a weight vector, W, that when I put it inside every single G, every single constraint, is giving me some negative value, right? This is the constraint that I want, correct? So I need a weight that when I put it in the constraint function, it's negative, correct? Now, if I do that, if I put that G inside this dual Lagrangian, and you keep it in mind that all of those lambda values are positive, what's going to happen to this dual Lagrangian function? It's going to be some function f plus lambdas are positive, correct? G values are negative, correct? So that summation, is it positive or negative? It's definitely negative because every single constraint Gn that you have is going to be negative, right? Every single lambda that you have is going to be positive. So every single term inside the summation is negative. When you sum them up, it's again negative, right? You have your function f, you add a negative value to it. Is it going to increase or decrease? It definitely decreases, right? So it's decreasing. So what you can do, what you can say, if you want to maximize this term, this Lagrangian term, with respect to lambda, what is the maximum value? You set all the lambdas 0, and then what's going to happen? What is the maximum value? F function, the objective function itself, right? So the maximum value that you can get is the f function itself in this case. So I can say, when I am looking into one feasible point, then the maximum value that I have in this Lagrangian function over all possible dual variables lambda is going to be the objective function itself, correct? Now, let's get into another case. The next case is that when I have infeasible point. And by infeasible point, what do I mean? There exists at least one guy who is not giving me 0 or negative constraint, is giving me a positive constraint, right? So say, for instance, the way W is chosen inside that, the first constraint is deviated. If this is the case, it means that when I compute this first G value, G1, it's not going to be 0 or negative. It's going to be positive, right? So say G1 of W is positive, right? This happens, okay? This is one point. That point is definitely infeasible, right? Because it's not satisfying the constraint, correct? Now, if I want to look for one choice of lambda to maximize again this term, what would be that choice of lambda? Say I set all lambdas, lambda 2, lambda 3, everybody 0, okay? Then that Lagrangian is going to be the objective plus lambda 1 times G1. And then lambda 1 and G1, they are positive, right? Both of them. So their multiplication is again positive, right? So I'm going to have some Lagrangian of this form. So my Lagrangian in this case, L of W and lambda is going to be F of W plus lambda 1 times G1 W, right? So this guy, what's going to happen if I put some, if I increase the value of lambda? Is it going to increase or decrease? It's going to increase, right? So what would be the maximum value then? Infinite. Great. So if I have even one single constraint being violated, then the thing that is going to happen when I just maximize this Lagrangian, then I'm going to see that the maximum value is infinite, right? So this Lagrangian has this property. If your point, W, is feasible, is satisfying the constraint, its maximum value is the value of your objective. If it's infeasible, it's not satisfying the constraint, its maximum value is infinite. So I can just put these two things next to each other. So what I can say if the first line happens, like everybody is satisfied, every constraint is satisfied, so I have a feasible point, then the maximum of my Lagrangian is the function itself, right? If even a single one is not satisfied, then the maximum of my Lagrangian is infinite. Now, if I minimize this function over W, what's going to happen? What do I get? If I minimize it with respect to the weight, to the W variable, what's going to happen? can I have in my solution an infeasible point? Can I have it if I minimize this function, this new function, which looks like this? If I minimize it against W, can I get an infeasible solution? If my solution is infeasible, then what would be the objective function in that case? What would be this L function, Lagrangian? It's infinite, right? So it cannot be the minimum of the function, because the minimum of the function cannot be plus infinite, right? So what is the minimum of the function? It's the minimum of f function itself, but among the points which are feasible. Everybody seeing that? Yes or no? Yes? Great. So if you see this, what you can say that if you want to minimize this guy against W, then this simply means that you need to make sure that you are on the first branch of the line 1, the first equation. And this means that you need to have a feasible point, and at the same time, you need to minimize your objective function, which is essentially the constraint problem that we want to solve. So moral of the story, if you make that Lagrangian dual, and then you maximize it over the dual variable, and then you just minimize it over the variable that you have, you essentially end up with the solution of your constraint problem, right? But the key point here is that this new problem is not constrained anymore, right? So when you are solving it, you are not looking to any feasible region. You basically just minimize over every W that you have, right? So we can, instead of solving the constraint problem on the right-hand side, we can simply just solve the unconstrained problem on the left-hand side. And this is what we call it the primal problem. Okay? The primal problem is exactly the same problem as the constraint problem. So we wanted to minimize a function given a bunch of constraints. We just make the dual Lagrangian. And then if we first maximize this dual Lagrangian with respect to the auxiliary variables, and then we minimize it with respect to our primal initial variables that we have, in this case W, then we're going to see the minimum of the constraint problem that we want. It's exactly the same thing. Primal problem is same as the original constraint problem. Everybody's clear? Now, it turns out that this is not that easy to solve because the original problem, the constraint problem, was not easy to solve. So what can we do instead? It might be easier that we just flip this minimization and maximization. We first do the minimization over that primal variable that we have, and then we maximize it over the dual variable. So we can just switch this minimum and maximum, and then there is no guarantee that we end up with the exact same solution as before, right? Because we are not following the same pattern, right? We're first minimizing with respect to W, and then maximizing with respect to the dual variables. Yeah? This is what we call it the dual problem. Yeah? It's not exactly as the primal problem that we had. It's a dual problem. Everybody's clear? Everybody's cool? Yeah.
So by solving the dual problem, is the answer going to be like S? It's always
I'm going to say the next slide. So you're going to bound the original answer.
I was going to say, like, is it
It's always smaller.
like we're going to get worse than the primal problem?
We're going to get smaller than the primal problem. You're right, because you're just changing the order, right? Yeah. You can easily show it by 2 lines, right? So everybody's clear? The difference, primal and dual? Okay. So now, what is the property of this dual problem when we compare it to the primal problem? The key property of this guy is that this d value is the value you get when you solve this dual problem. P value is the value you get when you solve the primal problem. And you can simply show that this is quite easy. You just spend a few minutes, and you're going to see that when you switch this minimum and maximum, you're going to get, in general, a value which is smaller or equal by the primal value you get. Okay? So if you solve the dual problem, you get into one value, which is bounding your original primal solution from below, right? You are going to be somewhere below it. Yeah? But this is not the most favorite case that we are looking into. The most favorite case that we'll look into is the case when we have the so-called strong duality. What is a strong duality? Strong duality is going to happen when you have your objective. It means function f being convex. So convex, if you remember, we talked about the convex function. It looks like a cup, right? It's going to always go up, right? So that function is a very nice function. So if you have a convex objective, if you have your constraints also convex, this is the second thing, and you have a bunch of feasible points. So it's not like the problem has no solution or every single solution is happening in the boundary. Okay? If that is the case, so simply speaking, if everything is convex and always going up, then we have a strong duality. And what does this strong duality says? It says that d value and p value exactly meet. They are exactly the same thing. So you don't need to solve the primal problem. Just go ahead and solve the dual problem. And whatever you get out of it is going to be the solution of your primal problem. This is very good, right? Now, in our case, do we have these properties? What is our objective? Is the norm squared, right? Norm is squared, and a squared function. Is it convex or not? Yeah, it's going up, right? So objective is convex. What about the constraints? This guy. Is it convex? It's a line, right? A line is always convex. Huh? It's even better than convex. So this is convex. This is convex. So we are good. Okay? We can use a strong duality. Meaning that if we solve the SVC problem using, the dual problem of SVC problem, then we're going to end up with the solution of that guy. So everybody's happy? Shall I go on? So now, if you want to solve the dual problem, it's going to get solved much easier than you think. So you really don't need to solve the minimization first and then go for maximization after. You can do it. You're going to find the solution. No problem about that. But you can do it easier using what we call it the KKT conditions. Okay? Now, what is the KKT condition? The KKT condition is that it says that, say W star and lambda star are the solution of the dual problem. And I have in the dual problem two solutions, right? I have W star, which is the optimum point for weight, and I have lambda star, which is the optimum dual variable, correct? Because just get back here. So we have one minimization happening over W and one maximization over lambda, right? So my optimal point is both containing both W and lambda, correct? So now, that point, if you put it inside the Lagrangian function and you compare the gradient with respect to the weight, that gradient should be always 0. Doesn't surprise you, right? Because this is a stationary point, correct? So it should be the stationary point of your objective. You do know that at the optimal point, the gradient is 0, right? So this should happen, okay? This is the first point. This is what you usually do even if you have an unconstrained problem, right? The next thing, it should be a feasible point. Again, doesn't wonder you, right? It's not surprising. It should be feasible, the solution. But the last thing, which is going to help a lot, is what we call it. Why I have written supplementary slackness? It's complementary slackness. So it's a complementary slackness. So what is the idea of complementary slackness? It says that those dual variables, those lambdas that you have, if you find the optimal ones for that, and you find the optimal W, then you put the optimal W inside the constraint and multiply it with the corresponding optimal dual variable. This should be 0. And it's not something super complicated. It just comes out of computing the stationary point, setting it to be 0. Okay? Now, what kind of property is that? Why this is important, this complementary slackness? So, let's see why this is important. let's say that this guy should be 0, okay? And say that the point, this W star point, is, for one particular constraint, is on the boundary. Let me see first. Yeah. Is on the boundary. What does it mean? My constraint, what is my constraint? My constraint is that Gn W to be less than or equal by 0, right? So I want this happen for every single n. Now say for one of those constraints, this is happening exactly with equality. Okay? So this is still valid, right? Because it's satisfying the constraint. Now, say when I compute my optimal point, this happens. Now, if this is 0, what could be the value of lambda n if I want the complementary slackness to happen? What should it be? It should be anything non-negative, right? If it is 0 or if it is non-zero, then essentially the product is going to be 0, right? So this guy is 0. Whatever that guy is, there is no problem, right? Everybody's cool? Now, what if this guy is happening with a strict inequality? What if this is not 0? I'm not on the boundary in this constraint. Then lambda should be, this is the optimal one. Lambda n star should be 0, right? So what it says, I mean, in practice, this guy, I mean, the equality does not happen as well here. What it tells you, it says that if the point that this W star that you find, it is anywhere on the boundary of the region you can have your feasible points, then its dual variable should be non-zero. And this is essentially that non-zero value is telling you that your constraint is active. But if that constraint is happening with a streak inequality, this means that your optimal point is already inside the region. It is not on the boundary. And then your dual variable is going to be 0, meaning that that dual variable is inactive. Okay? So when the constraint is 0, we are on the boundary, then the dual variable is active. When we are not on the boundary, when we are inside the region, then our dual variable must be 0, meaning that that dual variable is inactive. Now, what does this active and inactive mean? So I'm going to show you one example. You're going to get the idea more clear. But in simple words, when your dual variable is active, it simply means that that constraint is important. Like if you don't have that constraint, your solution is going to change. But when one constraint is inactive, when the dual variable is 0, this simply means that just drop that constraint. Nothing going to change your problem. Okay? So let's see one example, and then this is going to help you to understand this idea. So I want to minimize this function. So this is same function as what we have in SVC. I want to minimize this function. And for this guy, I have this single constraint. I want W1, the first entry of it, to be less than or equal by 1. Okay? Everybody's clear? So now, first of all, how does the function look like? How does the function look like? So we had it last time. We played around with it. We computed the gradient of this guy. This is the three-dimensional surface like this, right? Correct? Now, you have, say, for instance, W1, W2, and then what you need your W1 to be smaller than 1. So meaning that if this is 1, the value 1, then you need to just look at the points which are behind this region, right? So this is W1. This is the wall of W1 being equal by 1. You should think here, right? Any point after that is not inside your feasible region, correct? Now, before I start solving this problem, Do you think that constraint is doing anything here? Forget about the constraint, W1 being less than 1, okay? And now, what is the solution? What is the minimum of this bowl? What is the minimum of this guy? It's happening at the origin, right? Your weight being 0, right? So if I put weights to be 0, W1, 0, W2, 0, my function is minimized without the constraint. Is that point satisfying the constraint? Right? So W1 is 0, which is smaller than 1, correct? So essentially, I don't need that constraint, right? So now what do you think? Do you think that if I solve the dual problem, at the end of the day, do you have any guess what's going to be the dual variable? It's going to be 0, because this constraint is actually inactive. It's not doing anything on my optimization, okay? So let's look at it first from like simple point of view, visual point of view. So if I don't have the constraint, then the region, the point 0, is going to be my solution. This solution is satisfying the constraint. So this means that this is the solution, right? I don't need to just think about the constraint at all, right? Because my global minimum is exactly in the region that I can work in, right? But if you try to solve it using the dual Lagrangian, then the thing is that you first need to just write down this constraint in the standard form. So I want to write it down in the form of Gn being smaller than or equal by 1. I do have W1 being smaller than 1. So I'm going to take this guy the other side, make it 0. So this is now my G1W, right? So this is my constraint, and I have just one constraint, right? So I'm going to get that constraint. I add it up with that variable lambda to my objective, and this is going to be my dual Lagrangian, right? Now, first thing what I do, I minimize this guy against W, right? Now, if I want to minimize it against W, what should I do? I find the stationary point, first constraint in the first condition in the KKT conditions, right? So I compute the gradient with respect to, anyone? I compute the gradient of this Lagrangian with respect to W, great, and I set it to equal to 0. Great. So let's do it together. So you compute the gradient. The gradient, the first partial derivative, W1, is showing up in the first term and in the condition, right? So it's going to be 2 times W1 plus lambda, right? So this is the first partial derivative. The second partial derivative, W2, is only showing in the second term, right? So it's going to be 2 times W2. You set it equal by 0. What you conclude? You conclude that your optimal W1 should be minus lambda optimal divided by 2, right? And your optimal W2 star is going to be 0, right? Everybody's cool? Compute the gradient equal to 0, right? Now, next thing that we are going to do, we are going to check the feasibility, right? We want the points to be feasible. And to be feasible, it simply means that I want the constraint to be satisfied. If I write down my W star, I mean my W1 star is now given in terms of lambda, right? I'm going to replace it inside my constraint, and I make sure that the constraint is satisfied. So it's going to tell me that my lambda star should be more than minus 2, right? On the other side, I do know that in the dual problem, I need lambda to be always non-negative, right? So this is the other constraint. Both of them together are satisfied when my lambda is non-zero, right? Sorry, lambda is non-negative, right? So in order to have a feasible solution, I need my lambda star to be non-negative, right? So this is the second condition in the KKT conditions. And the last one is this complementary slackness. So if I want to check that guy, I am going to just set this lambda star. This is the one which I compute, my optimal one, times my constraint to equal to 0, right? And my W1 star, I do have it in terms of lambda star, right? W1 star is simply lambda star half minus, right? So I'm going to replace it here. And if you do the math, you're going to end up with this equation. And you want to solve it in terms of lambda star, right? This is going to have two solutions. One of them is 0. The other one is minus 2, right? And minus 2 is not acceptable because you want your lambda star to be non-negative. So only 0 is acceptable, right? So solution out of this complementary slackness is going to be lambda star equal by 0. Everybody's clear? Yep. I mean, initially when we had the dual problem, where is the dual problem? Yeah. Here we have the constraint. Every single lambda should be. That's the definition, yeah. The constraint will always have it on the dual variable. Because if you don't have it, I mean, this property that one of them is plus infinity, the other one is f, is simply coming from the fact that lambda is negative, not negative. If lambda is negative, then in both cases it could be, it could simply get plus infinity.
And when we introduce lambda, how do we think of introducing the lambda? Or this is kind of a
No, this is, I mean, this is the trick that we call the Lagrange multiplier. But this is coming from the idea of making a barrier method. So this means that when you have a function which you want, like, say I have a function, I want to minimize it in one interval, right? But I don't like to always think about that interval. The thing that I can do is that I can set my function to be the same in that interval, and then define it anywhere out of that interval to be infinite, right? And if I minimize this new function, which is not constrained anymore to one interval, I again end up with the same solution, right? This is what we call the barrier method. And then Lagrange multiplier, or dual Lagrangian, is something that when you maximize it over your dual variables, is making a barrier for you. Yeah. But the cool thing about it is this, duality result, the KKT condition, which helps us solve the problem more efficiently. No. Any questions? Okay, so let's get back here. So that is the final thing about lambda star. So out of this stationary point, being in a stationary point, we could find the optimal weight in terms of lambda. Out of feasibility, we could just constrain the region where lambda could belong to. And finally, out of this complementary slackness, we could compute the exact value of lambda, right? So the problem is solved. We can just replace that lambda into the expression we had. The solution going to be 0, 0. And the optimal dual variable is 0, which says that the constraint is inactive. It's no surprise because we did know that that constraint is pretty much doing nothing, right? Everybody's clear? Now, one other case that we could have is the case where we have I wanted to say, please just be quiet, but there were too many people. So I got afraid, so I didn't say anything. So, yeah. So this is the case where the dual variable is inactive, right? Now, let's just think about the other case. The other case is this problem. So it's the same problem as before, but now I need my W1, instead of being less than 1, being less than minus 1, less or equal by minus 1. So now, if I think of this problem, do you think that I still get the origin as the solution? No. Why? Because the origin is not satisfying the constraint, right? So basically you have the ball, but you are limited to a region where this origin point, this 0 point, is not belonging to, right? Now, intuitively, what is the solution of this guy? Right on the border, right? So the solution would be exactly at the border. You can simply see that, W2, I can just minimize it as I wish, so I'm going to put it 0. W1, I cannot go more than minus 1, right? So I'm going to put in minus 1, right? And then the solution going to be minus 1 and 0. And this is one point on the border, right? Now, what do you think about the dual variable? Should it be 0 or should it be something non-zero? It should be non-zero because your constraint is now active, right? So this constraint is really impacting your solution. It's active, so the dual variable should be non-zero. So let's look at it again together. So the solution is obviously not the origin because we do see that the origin is infeasible. And we can simply see that the solution is on the boundary. Now let's solve the dual problem. So if we solve the dual problem, again we're going to add up that constraint. So we take that minus 1, bring it to the other side. It's going to be W1 plus 1. This is the constraint now. We're going to add it up with one Lagrangian, with the one dual variable lambda. And now we try to find the stationary point of this dual Lagrangian, right? And if you find the dual stationary point, you're going to see that the stationary point is going to look like this one, right? You just compute the dual variable, so it's the same thing as before. So your dual, you find the gradient and you set it to be 0, then W1 star is going to be minus lambda star half, and the other one is obviously 0, right? Everybody's cool? It doesn't change. It's exactly the same thing we had in the other example, right? Now, the next thing. I'm going to check feasibility. So the feasibility wants me that this point W1 star, which is now I'm replacing it with minus lambda half, this guy should be less than minus 1. So if you do the math, this means that your lambda star should be more than or equal by 2, right? So if you want the constraint to be satisfied, you need your lambda star to be more than or equal by 2, right? And of course, you need your lambda star to be more than or equal by 0 as well. This is the dual condition, right? Now, if you just merge these two constraints together, you're going to conclude that your lambda star, whatever it is, it should be more than or equal by 2. So it cannot be 0. And this is obvious to you because the constraint is active. It cannot be 0, essentially. It should be something more than 0. At least it should be 2. Everybody's clear? So finally, you just try to find the complementary slackness condition. So you put that W1 star into this expression for the slackness, and then you set it to be 0. Then you're going to see this equation. This equation is going to be 0 if your lambda star is 0 or 2. And you know that you cannot take the solution 0 because your lambda star should be more than 2. So you're going to take 2, right? Correct? Now, you're going to end up with lambda star 2. So your solution is when you put, just get back here, when you put lambda star here to be 2. And when you put it 2, it's going to be minus 1 and 0. So this is going to be the final solution here, minus 1 and 0. And what you see is that your solution is happening on the boundary, right? And your dual variable is non-zero. Everything is matching or intuition. Everybody's clear? So, moral of the story, the whole thing is that as long as one constraint is not doing anything, I mean, if you want to solve one constraint problem, as long as you see that the optimal point that you find is really in the feasible region, you don't care about those constraints, right? The only point that you see you need to take care of the constraint is when that point is not inside the constraint. And actually, you could start from that point and just move towards the boundary, and you get to the point that is your solution, right? And those dual variables is going to tell you how much you need to just get away from that point to get into the boundary. So that's it for constraint optimization. Any questions on that? So everybody's happy with this dual Lagrangian? So if you have a problem which has constraint, you always can add these constraints with Lagrange multipliers into your original objective. You try to minimize that guy, and then you find the lambdas which are maximizing that solution. Then that solution is going to be the solution of the original one, assuming that those Slater's conditions are happening. Okay? Strong duality is happening. Okay, now let's get back to our own problem. So our problem was to minimize that weight, so W squared, that norm of the weight, and then our conditions, we had n different conditions, and every single of them looks like this, right? Now, once again, I can just write it down in the standard form. So I'm going to play around with that condition to just write it down as one term less than or equal by 0. Okay? Now I have the standard form. I have my objective. I have my constraints. And we talked about this. Both of them are convex, right? And we definitely have enough visible points. So strong duality is happening here, meaning that we don't need to solve this constraint problem or the primal one. We can simply solve the dual problem, right? Everybody's clear? Any question? So let's go for the dual problem. So Slater's conditions are happening. So since they're happening, we can solve the dual Lagrangian. So we basically make the dual Lagrangian function, which is our objective function, W squared, plus summation of dual variables, lambda n, multiply with the corresponding constraint, right? And these lambda n's, all of them should be, lambda n's should be non-negative. They should be 0 or positive. They cannot be negative, right? So that's the only thing we need to care about, right? And then we need to solve this. Now, if we start with solving it, what should we do? Let me do it first on the board for you. So that is going to make it easier to see. So my Lagrangian is that guy, and I want to compute the Lagrangian gradient of this Lagrangian and put it equal to 0. So what is the gradient of my Lagrangian? What is it? The gradient of the first term. We did it before, right? So this is norm squared. What would it be? The gradient would be 2 times the weight itself, right? So the gradient of the first term is going to be 2 times W, right? What about the next term? What would be the gradient of the next term? I mean, lambda n times 1, if you compute the gradient with respect to W, it's going to be 0. So it's not going to show up, right? Lambda n multiply with that term. This is inner product of W with one vector, right? And the gradient is that vector itself, right? So it's going to be minus summation of lambda n times, x n. And we have this Vn as well. I mean, this scalar is going to also show up, right? And going from 1 to n. Everybody's cool? Right? So now, if I set this guy equal to 0, what's going to happen? Your W is going to be this guy divided by 2, right? So I want to set it equal by 0. This means that I'm going to end up with this solution. So my W star is going to be 1/2 this guy when computed at the point lambda n star, right? Everybody's cool? Any questions? So, again, we have it in this slide. So if you compute the gradient, then the gradient of the first term is 2 times W, minus the gradient of the second term is this summation. You set it equal by 0. Then W star is going to simply be this summation divided by 2, right? Now, before I proceed, just look at this W star that you are finding. And we don't right now care about what are these values. What is it happening here? What is your weight? What is your optimal weight? I can think of everybody here. This 1/2. This is also one scalar, right? This is also the label. This is plus or minus 1, right? So let me just take all of these guys and I call it one weight, one, I don't know, alpha n. What is happening now? Is summation of this guy, this is then simply summation of alpha n xn, right? Correct? So your optimal weight is a superposition, a linear superposition of your data points. Everybody's cool? So this is what it says, but how you can find those weights of this superposition, you need to find the dual variable, right? Once you find the dual variable, you get what is the optimal weights. Any questions? Everybody's cool? So, moral of the story here, your optimal weight is going to be some sort of average of your data points, but those weights that are participating in this averaging, you still need to find it. Okay? How can I find that? So what I did here is the stationary condition, right? What should I do to find them? I can either take this W star, put it in my Lagrange dual objective. Now I find one function in terms of lambda, right? And then I try to maximize it. This is one solution, right? The other way of doing it is to just check the feasibility constraint and also find the check the complementary slackness. And the point which satisfies everything is going to be the solution, right? This is the other way that I can do it. Correct? But it doesn't change the fact that the solution that I find at the very end of the day is going to be the average of my data points, right? Everybody's cool? Okay, so let's go ahead, do this. So one thing is that I can take W star and I can fit it into the function. So I have this W star, which is that summation, right? I get this W star, put it back here. So I compute its norm, and also I put it there inside that second term, which is the constraint term. And if you do that, you're going to end up with this expression. I'm not sure if everybody's seeing it immediately, but if you don't see it, just trust me. I did it before. So this is correct, okay? I don't want to bore you, tire you with all of the details. You can try it at home if you wish, but you're going to end up with such expression. And what should I do to that expression? If I want to find the optimal values for dual variables, I can maximize it, right? Over all dual variables which are non-negative, correct? This is one way that I can do it, or I can check the visibility and complementary slackness. Both of them are correct. Both of them are the same thing, okay? Now, one thing that you can look at it here is that your optimal weight that you need to find, or optimal dual variables lambda that you need to find, is depending, when you want to put something from your data set there, you basically need to put those green terms, right? Correct? So when you have your data points, you essentially don't need to get your data point itself, but you basically need the inner product of every single data point to another data point, right? And you should consider all possible cases. Once you have all of them, then you can make this summation here, right? And once you make this summation, you can solve it in terms of lambda, correct? So this is one point that you should pay attention. We're going to use it later on. So if I make that guy, then I am going to just solve this maximization problem. And as I told you, here this maximization problem is only depending on the green term, right? And the green, from the data set, you only need that green term, right? So meaning that you don't really need to have the data points, the samples themselves, but you need their inner product with other samples, right? Correct? So you start from the first data sample, you compute its own inner products, which is its own norm. Then its inner product with the second guy, inner product with the third guy, inner product with the last guy, right? First point over the second point. Its inner product with itself, its norm, next guy, next guy, next guy till end, right? And you compute it for every single possible pair. If you do that, then you have all the things you need to solve this problem. Correct or not correct? Yeah? So if I don't see the vector itself, I'm still fine, right? I can still make this summation. It's important to see it, because if you don't see it, then we cannot simply fly to the SVM. Everybody sees that? So if I don't have the vector itself, so x is a vector. This vector could be 1,000 dimension, right? It could be 1 billion dimension. I don't care about its dimension. As long as I know its inner product with everybody else inside the data set, and those inner products are simply scalars, right? As long as I know all of that, then I can make this summation, right? Because I can put all of those inner products inside this summation and then do the summation. And finally, I need to maximize it over lambda, correct? So for finding lambda, I don't need the data points by themselves. I just need the correlation between the data points, right? Everybody's cool? Yeah.
Can you explain why is it not dependent on the lambdas and the v's?
No, it depends on lambda and v. I don't say that it doesn't depend on that. What I say is that if you have data set, and this has lots of long vectors, right?
You only need to know
The inner product of those vectors. And once I have it, I can put it inside this expression. Now it's a function of lambda, and I can try to maximize it, right? Okay? Everybody's clear?
Why would you know the inner product?
We're going to talk about this, but I mean, at this point, we think that, okay, we have the vectors, we compute the inner products, right? But if somebody comes up with and tells you that, okay, you don't need I don't give you the vectors, I just give you the inner product, you still can do it, right? Yeah? Okay. So, now, if one other possible case is that instead of just maximizing this expression, I just go ahead and check the feasible solutions and then try to apply this constraint of complementary slackness, you're going to end up with the same thing, okay? So it's no different. You're going to, at the end of the day, end up with the same thing, that you're going to see that your complementary slackness solution is only depending on these, inner products. And there is one key observation that we do here, which says that the optimal model, it means that the choice of lambda star that we need at the very end is going to be characterized only via the cross correlation between the data points, okay? This inner product is what I call it, the cross correlation, okay? Everybody's clear? So, just keep it in mind, right now it's not impacting anything, but when we start with SVM, it's going to help us a lot, okay? So, now let's go ahead. You can also, as I said, try to just check the complementary slackness, and in that case, you're going to end up with the same expression, because that W star is going to contain all of those xn's, and when you just transpose it and multiply it to every single xn, you're going to get, again, a bunch of inner products, okay? You're going to see the same expression as before, okay? So, now, why this happened? Oh, no. Okay. Anyways, so now, if you want to solve this complementary slackness constraint, or if you want to solve this optimization problem, you really need to know those value of the inner products. You put it here and you solve it, right? So I cannot give you the closed form solution directly for those lambda stars. The problem is solved. Just you solve this problem, take those lambda stars, put it here, and then this is going to be your weight, okay? That's it. The problem is solved. But if we use the complementary slackness, then we know one thing about the lambda star. What is that thing about the lambda star? So, if I don't want to solve the problem, I do know that these lambda stars are the dual variables, right? Now, when is the dual variable non-zero? The dual variable is non-zero or active when the constraint is happening with equality, right? The constraint, we talked about this, if the constraint happens with equality, then our dual variable is non-zero, right? This is the complementary slackness condition. So if you find the solution, that solution should definitely satisfy this constraint, okay? This is going to happen. It's not like you make it happen. This is happening by itself, okay? So what I can say is that if my constraint is happening by equality, then my dual variable is positive, right? If my constraint is happening with a strict inequality, then my dual variable is 0, right? Okay, that's good. So we do have these two things, like the constraint is active, then we're going to have lambda non-zero. If the constraint is inactive, then the lambda is 0. And active and inactive simply means that whether we are on the boundary or not. But which points have this constraint in the SVC problem with equality? Yeah, go ahead. The support vectors, great. Yeah, everybody remembers? Let's look at this guy. So we said that the support vectors, right, are going to have the constraint with equality, right? And everybody else is having the constraint with strict inequality because they are the points which are far away from the boundary, right? Only support vectors are the closest one, and all of them are having this constraint with equality. So this means that the dual Lagrangian, the dual Lagrange variable of every single of those support vectors is going to be positive, great. And for those who are not support vector, it's going to be 0, right? So look at this again. So for every support vector, we're going to have non-zero lambda star. For every point which is not support vector, then we are going to have 0, right? Everybody's cool? Any questions? Well, let's take that guy, this result, and put it inside that summation that we had. So we had the summation. I mean, okay, I have dropped this 1/2. It's not really important. Just look at it here on the board. W star is going to be the summation of all of these lambda n stars, Vn times Xn, right? For those who are not support vector, this lambda n is going to be 0, right? For those who are support vector, this is non-zero, right? Now look at this expression, this alpha n here. When is it non-zero? When is alpha n non-zero? Alpha n is simply this, red box, right? It's going to be non-zero when your vector is your data point is a support vector. Great. So what you can say at the very end of the day, you can say that you are doing a sort of summation over your support vectors, right? So you are finding a kind of average of your support vectors, and those support vectors are going to specify the direction of your weight vector. Everybody's clear? Any questions? Any question? So as I said, I have missed 1/2 behind everything here, but it's not going to change the fact, right? So, yeah.
How do you know which of the vectors are support vectors?
Yeah, you need to solve the dual problem, right? Yeah, I'm not solving it because I need the exact data set. Once you solve it, you find out which the guys are support vectors. So it's not changing the complexity of the problem. The only thing I want to show you here is intuitively at the end of the day, you're going to find a bunch of points which are support vectors, and your weight is going to be average of these points. Yeah? Yeah, but you need to solve the dual problem. Yeah.
Sorry, did we not check the feasibility?
Yeah, this is equivalent to this one. So you can either solve this maximization. When you solve this maximization, you already check the feasibility in the constraint. And the other feasibility is obviously going to happen inside this maximization. Or instead of solving this maximization, you can do feasibility plus complementary slackness.
Yeah, I mean, like on the next slide.
Yeah. Yeah, I have written here, it describes system of equation that is solved uniquely via feasibility constraints. So you're going to have, I mean, when you put this equal to 0, for every single n you have one equation, right? And all of them have these lambda values from lambda 1 to lambda n, right? So it's a system of equations. And then you set it equal by 0, you're going to end up with a couple of solutions, right? And there are just one solution which is visible. Everything else is not visible, given the primal and dual constraints. And that solution is the solution of your, or giving you the lambda star, and also is going to specify your support vector. Okay? But you don't need to solve it. I mean, if you want to solve it, you really need to have the data set, right? Because you need to know the value of this x and, I mean, these inner products, right? You really need it. When this change, the value of lambdas also change. So I cannot give a compact solution to you. It's going to be a numerical thing. But what I do know is that when you solve it, you're going to have a bunch of zeros, which corresponds to those vectors which are not support vectors. And we have a bunch of non-zero entries, positive entries, which are corresponding to the support vectors. Okay? Any questions? Okay. No question. So let me just finish this part, and then we're going to have a quick break. So as I said, so basically what is going to happen is that the support vectors are showing in your final expression, and what you can write it down in this form. So this is the main reason that we call it the support vector classifier. It means that when you solve the dual problem, you're going to end up with a bunch of points which are going to be very close to your boundary. And these are the support vectors. And if you know those support vectors, you can essentially compute the weight as the sort of averaging of these support vectors. Right? Yeah. Now, if I want to explain you in conclusion how we can do the support vector machine optimization, the first thing that you are going to do, you need the cross correlation between every single pair inside your data set, right? So any 2 points you think of in your data set, you compute the inner product of them, right? Once you have all of these inner products, then the next thing that you should do, you are going to find lambda star, right? So when I have these inner products, I can just replace it inside this expression and try to solve the optimization problem, right? So you can essentially do that. So once you have the inner product, you can find lambda star. And these lambda star are going to be, some of them are going to be 0. These are the vectors which are not support vectors. Some of them are going to be positive, and they are the vectors which are support vector. And then your weight finally is going to be average of those support vectors. And how do you average them? You just do it by lambda star, right? So that's the solution to the SVC. Problem solved, right? Now, what's going to happen when we do the invariance? So, meaning that I went on, so let me write it here. I went on and solved the problem, right? I went on and solved the SVC problem. So I got my cross correlations. I put it inside the dual problem. I found lambda star, right? Then at the end of the day, I am going to have my W star being 1/2 summation of lambda n star Vn xn, right? And we do know that these guys are going to be non-zero only for my support vectors, right? Okay, great. Now I'm going to have this. Now, I give you one new point, x, which is out of your data set. What do you do to that point? If I give you a new point, x, out of your data set, and I want you to use your support vector classifier to classify it, what do you do with that?
Take the dot product
With W, great, and then?
So that would be a dot product with respect to all different x's of the data.
Yeah, sure. For the moment, just, I mean, say I give you W star. What do you do to that? Multiply, and then you check the sign, right? If sign is positive, you say the label is 1. If sign is negative, you say the label is -1, right? Okay, so this means that you are going at the end of the day to get this guy transposed, multiply with your new point x, right? Everybody's clear? Now, this guy transpose, this W star transpose, it means that this whole thing transpose, right? And if whole thing is transposed, what is happening? These guys are untouched. This one, these vectors are going to be all transposed, right? So transpose times x, right? This is going to be the thing that you check its sign. Everybody's clear? So if you have a new x, you're going to transpose this summation, which simply means every single accent inside this summation needs to be transposed, and then you multiply everything with x. Everybody's cool? So I have it here for you. So y is going to be W transpose times x. Your W is going to be this summation and transpose, and it's multiplied with x, right? Now, in this expression, do I need to know x itself and xn itself if I did know what is their inner product? No, right? So I only again need the inner product of x and xn. And which xn? Do I need the inner product with all xn's inside my data set? Just the support vectors, right? Because lambda n for anyone else is 0, correct? Cool. So again, what we see is that we only need the cross correlations, and this is the whole idea of the support vector classification. So if I want to just give you a bit of visualization, say these are our data. This is obviously linearly separable, meaning that I can draw one line where every red point is on one side and every green point is on the other side, correct? So now if I want to find that line, side that my margins is maximized, what should I do? I am going to first look at the cross correlation between every single pair, right? I compute the cross correlation between every single pair of data points, right? So if I compute this like I start with this point, this first point, say this lower red point, compute with the first neighbor, second neighbor. I keep on going till I find this cross correlation with the last neighbor, right? And then I go for the next point. I do the same thing till the very last one. Say this is the last pair I check. Now I have all the cross correlations inside my data set, correct? Now that I do have, I can find the support vectors, correct? I just solved the dual problem. And say that you do this and you find out that these guys are the support vectors, right? Okay? These guys are the support vectors, meaning that your line, the line which is going to just do the classification for you, is the linear combination of these guys, right? So basically it's going to be the dual variable of the first guy times x1 plus dual variable of the x2 times x2 with its own sign, which is -1 here, and then the last dual variable times x3. Correct? This is going to be your weight vector, right? Now, if you get a new sample point, what you gonna do if you want to classify it? But you basically, I mean, of course, if you have the weight, you're gonna do the inner product and you check the sign, but you can think of that operation in this form, that this new point that you get, you're gonna check it, you compute its cross correlation with the first support vector, its cross correlation with the second one, its cross correlation with the last one, and then you sum up everything, right? With the corresponding dual variables, right? And when you do that, based on that sign, you decide, right? Everybody's clear? Any questions? Yeah, go ahead.
SBC assumes that you already have a labeled data set, right?
You have a labeled data set, definitely.
And so in the case of, like this, for example,
Yes.
you have two data points which are positive,
Yeah.
and these are both the exact same distance from the line, which makes
Yes.
them both support vectors, right? Otherwise, it would just be one point from each respective side. Generally closest, right?
It's not necessarily the case.
Oh.
Even in the one-dimensional case. So you can think that like multiple points are happening at the same point, right? Multiple samples that you have.
Yeah.
Yeah? And then in that case, all of them are in the same distance.
Right.
So in this case, I mean, in this line case, you might have like lots of red points here far away from that orange line. And all of your green points are exactly in the same distance, right?
Yeah.
This is still going to be the same thing. You cannot say it unless you solve the dual problem.
Right. But really it just considers the two closest points though. Like it only considers the
Yeah, as long as we are doing it. If you have a soft margin, we have not talked about it here.
Yeah.
If you have soft margin, then you can consider like not only the first closest one, maybe a couple of other ones as well.
right. 'Cause I was gonna say, what if you have like a random red point on the opposite end now?
Yeah. That is the thing we talk about next. So if we cannot do really plot that line, then we need to do something else, which is going to be SVM. Okay? It's a good point. I mean, everything going to happen when you have everything separated, right? Yeah. Okay. Now, everybody is happy with support vector classification? So, moral of the story, you just need the cross correlations, right? You know cross correlation of your data set, you're going to find the correct weight. Once you have it, as long as you know the cross correlation of any new point with the support vectors, you still can classify it, right? That is the whole story. So this is why we call it support vector classifier, because we basically look into the support vectors. And this idea of checking, I mean, when we have a new point, checking the cross correlation with the support vectors, this is what we also call is cross validation, meaning that you get your point and then you validate it by comparing it to the guys who are closest. Yeah? So you check it with them in this form, and then at the end of the day, you get one invariance out of this cross validation, which is going to tell you whether the point is on this side or on the other side. Any questions? Everybody's cool? So you can check Bishop's or ESL textbooks if you want. I mean, the corresponding chapters. Let's have a quick break, say 7 minutes, and then we start with SVM. End of the session. Itself doesn't get marked. It's generally like rectangular. So it could be, so x is usually, this is your x, right? This is going to be all of your samples, right? x1 to x3. So this is n times d, and d is the size of these pictures, right? And in general, d does not need to be exactly the same, right? So this is not necessarily a square matrix, it cannot be inverted. Yeah? But when you do x transpose, then you have this guy. So you have x1 transpose, x2 transpose. Now this guy is n by d, right? And then when you multiply, it's d by d, right? What you can say is that when n is larger than d, with very high probability, this matrix is invertible. Because in that case, I mean, this makes sense. The number of samples that you have is more than the dimensions. And you, at the end of the day, you want to find W, which is a vector of dimension D, right? So you have D different variables. So if you want to find all of them, you need at least D different data points. Yeah, we definitely have pseudo inverse and we can find it. Yeah. Yeah. But if it is 0, then it's another story. So your problem is incomplete. You cannot even solve it. This is essentially not convex. But then there are tricks for that as well. North.
So, like the order of checking feasibility and slackness doesn't matter, right?
No,
Because,
it doesn't matter.
Because like slackness for just solving for lambda.
Exactly.
And then feasibility is like, there are some restrictions on
Yes,
how
exactly.
that
So you're gonna have multiple solutions here,
Mm-hmm.
and
then
then
we're
one
just
of them is
choosing
gonna.
the, choosing the ones that satisfy those. Also, could you explain again, why does like computing all the, sorry, why does computing all the inner products tell us which ones are the same?
Because when you compute all of those inner products here, you have the other slides here. So if you go back to the expression of the goal problem, if you no, even up, so when you want to do that maximization here, right? So if you know xn transpose times xn for any pair of n and m, you basically have this term, right? Now that you have this term, then you can get those cross correlation, put them inside this solution, right? And then you can solve it, which can give you the optimal lambda, right? And optimal lambda, when it's 0, it means that it's not a support vector. When it's non-zero, it can be the support vector, right?
Sorry, come again?
If you solve this problem and you form lambda star, all those lambda stars which are non-zero are specifying the support vector. Like for instance, if you find out that lambda 1 star is positive, then you conclude that the first x1 is a support vector, right?
But we'll have to solve this.
This, right, exactly. But if you want to solve it, this is a simple problem, right? It's a very simple quadratic problem. Yeah, you're always able to solve this problem. This is exactly like the example I solved for you. Because this term, this double summation, is proportional to lambda squared, right? And this expression is proportional to lambda itself, right? Just think about only one lambda. Then n is simply 1, right? Then this expression is lambda squared times the cross correlation of the 2 points with minus, and this is just lambda itself, right? So it's a quadratic problem. So your function looks like this. It's a parabola, and then you're going to take the top of it. If the top of it is not in the positive region, then you're going to just cut it in the positive region and take the boundary, right?
But we're going to do that with like every pair.
Yes, we're going to do it with every pair now, but it's still a quadratic problem in higher dimension. The only thing you need to write down this quadratic problem is these cross correlations, right?
Okay. Yeah.
Once you have them, then you can write it down, right?
Okay, so basically just plug in all the products with every pair,
Exactly.
check if the lambda is positive.
You don't need to check it, just solve this problem. Yeah? If the solution that you get is everything is positive, the problem is solved. If it is not, you go on the boundary, right? Or eventually you don't need even to solve this, just go for supplementary slackness, right? If you solve that one, it's the same thing again, right? The one you're easy, the one which is easier. But this problem, you can always solve it. Okay? If I want to solve this problem, so ax minus bx squared, and I want to maximize it over x, which is more than or equal by 0, I can always solve it. Because depending on a and b, this is going to just be maximum somewhere, right? If it is here, so this is negative part, so this is going to be the maximum guy, right? The one which is on the boundary, because this is not feasible anymore. If it is something like this, then this is the maximum, right? So the solution is simple to that. The point is that I need to know A and B, right? And A and B is specified with that cross correlations for me, right? Once you have it, then you know lambda, optimal lambdas, and then the optimal lambdas which are non-zero, then they are specifying the support vectors.
Okay, and then for testing it,
Okay?
we got the new.
New point, X. Yes, exactly. You found it in the role. Weights, the label of the support vector, which you know is and move on. Yes. The sign, exactly.
When you solve the dual problem, the dual problem is this guy, right? So once you just put x's inside this expression, you have one function. Sorry? No, not the new x, the x inside your data set. Then you can solve this problem. This is going to be a quadratic problem, you solve it. And once you solve it, you find a bunch of lambda values. Yeah? So they are going to tell you which one is support vector, which one is not. So you don't need to confuse yourself with that. Dual problem can take care of it. The only point is that you can intuitively think that you're only, at the end of the day, cross-validating your new point with the support vectors. If you have W star, okay, you just multiply it with the new point x, right? This is going to be your z value, for instance. And then if it is positive, you're going to say the label is +1. If it is negative, you're going to say the label is -1, right? This is the story, the whole thing that we did from the beginning. But the point is that we know this W star is summation of a bunch of alpha n's times x n's, right, inside our data set. So if I want to just multiply this transpose to this is like multiply x and transpose into x.
So we just cut the second line and find
Yes. Yeah, it's the same thing. Yeah. So they're the same. The label of this which is either plus or 1 or 2. Inside of the training is given to when we start the training. The data set is given positive by x1 with label plus. I will start with your
Yeah, for the project, is there any thing that you can't do for it, or is it just happening? Yeah.
No, you can't. I'm gonna post you after the midterms. Already you had one illustration running on your web. So it's okay as long as you feel comfortable. But you send me the proposal and then you give feedback.
Okay.
Alright, so if you feel like it doesn't sound to be feasible, then I could give you the feedback. By the end of the day, it's your choice. If you feel confident you can do it, you can try.
So could it be something like hardware related?
Hardware related?
Yeah, developing a CNN or
Okay, then you need to do experiments.
Yeah.
It is a part of you're working in a lab that you have this.
Okay. Right.
Okay, shall we go on?
Shall we go on? Okay. So one point. So for the exam, I will send you an announcement, but the exam is open book. So you can bring everything, not computer, not electronic devices, but anything printed, you can bring it. It's okay. Okay? So you can bring the printed stuff with you on the exam. So we are not taking history exam. Yeah. Yeah, I'm going to post you a couple of sample questions, okay?
Are you going to post requirements of what you need, what this form open book, what counts as open book? Can we just print out our notes?
Yeah, anything. So there is no limit. Bring the whole library with you. I don't think that you're going to use it, but you can bring whatever you feel confident and comfortable with. So if you have a bunch of formulas you can keep in mind, a bunch of examples, notes from tutorials, notes from here, you can always, but you need them to be printed on paper. Okay? That's no problem. So respecting the environment, I should have told you that you can bring your tablets, but this is against the policy in the department, so we cannot have electronic devices on the written exam. That's why I cannot do it. Okay? So, shall we go on? Okay, so the problem with the SVC, I mean, SVC is doing a good job in the sense that it's just maximizing the margin. The solution is quite intuitive. It explains us that we basically need to do a bunch of cross-validation. So we get our data set, we do cross-validation against the data set, we find out the support vectors. From then on, any new data, we're going to just do the cross-validation of the new data with the support vectors, and then we just classify this new data. That's it, right? So it's a cool thing, but the issue here is that this guy is still a linear model, right? Meaning that at the very end of the day, it's going to plot one hyperplane. Anything above this is plus 1. Anything below it is going to be minus 1, right? That's it. Now, can we solve every single problem with a linear classifier, any classification problem? Obviously, no, right? For instance, if in the cat or dog example we had, we get such a data set. Can I do it with one threshold? Obviously, no, because bunch of dogs are happening at high weights, bunch of dogs are happening at low weights, and the cats are in between. So wherever I put my threshold, I'm going to have a bit of error always, right? So this is not linearly separable, but can I still come out with some sort of nonlinear solution to this problem? I can, right? So I can say anything within that region is cat, anything out of that region is dog, right? So I can solve this problem with a nonlinear solution, nonlinear classifier. And what do I mean by a nonlinear classifier? It means that instead of computing the linear expression, so if you remember my z in the linear classifier, the z value which I compute in order to get into the in order to check the sign and classify my model, my data point, new data point, is going to always be a linear function. So in the linear model, always z is going to be my w, inner product with the data, right? I always check this. This is a linear model, but if I can just add nonlinearity to it, right? So I just, for instance, instead of computing simply w times x, I compute w times x plus w times x squared, right? Two different ways, one of them for x, one of them for x squared. This is no more linear, and if I can do it, definitely I can find a specific function which is going to be positive within that region of the green guys, and is going to be negative out of it. Okay? This is what I want to do. So this is also happening in higher dimensions, so not simply in our dummy example. For instance, here, again, you cannot think of any line which you plot and every green guy is on one side, every red guy is on the other side, right? But you can still come up with one nonlinear curvature which is going to classify them, right? So if I just get a curvature which is just surrounding all of the green points, this is not anymore a line, but this curvature, this curved region is going to be to specify or classify this data set perfectly, right? Now the question is that what can we do when we have such a scenario? And in practice, most of the time we have this story, right? Linear is too optimistic to happen, right? So usually you have such a story, and then the question is how we can do it. Okay? Now, this question was a quite long question. Okay? Starting from 30-something. So two people started, or two, say, ways of thinking on it were somehow developed. Not exactly in parallel, but through time independently. So one of them is the one which is nowadays known as deep learning. And the other one is the one which, in this VC approach, or this statistical learning, general machine learning approach was developed, right? But at the very end of the day, they got merged together, okay? And this is known as what we do know as deep learning. They are, any way that you start, you're going to end up with that answer, okay? But now, those people who study deep learning, they probably had that approach. So this is the way like Rosenblatt was thinking of, the perceptron machine, just going to make a network of neurons. This is the way that Vapnik thinks of, the SVM developer, right? You remember the pictures I showed you last time, right? Those two guys, the VC guys, they were thinking in this way. And this is very sophisticated. Take a look. Interesting thing is that at the very end of the day, this one is going to also get the solution of deep learning as well. So, say I have, let's get back to our cat or dog problem. So, if you remember in the cat or dog problem, my data points, x's, they were weights, right? And v was the label, for instance, -1 for cat, +1 for dog, right? And now, the thing that I now think of is that my data is not linearly separable. When I cannot draw a line which separate two classes completely, then I say that my data is not linearly separable. The problem cannot be solved by a linear model. Okay? I think that I have such an issue, right? Now, people started to think about 30 years, okay? And then after 30 years, they come up with this very brilliant solution. So what you're going to do, this is my axis x. You see it? This is where my data points is lying, correct? And on this axis, I cannot do any linear classification, correct? Now, what do? I'm going to add one extra axis to it, okay? I add one second axis, and what do? Whatever I have in this axis, I'm going to compute it squared there, okay? So basically, I have the function x squared. Any point that I have, instead of I just show x, I'm going to show x on the horizontal axis. On the vertical axis, I select x squared, okay? This means that what's going to happen to the first red point? If I do that, what's going to happen to that red point? It's going up, right? Where does it go? It goes exactly on that curve, right? So I'm going to show the first point, instead of being that red point on the x-axis, is now going to this two-dimensional plane, right? So the second point, again, goes on the curve, right? Correct? So this is the thing that is going to happen on the second point, right? So I'm going to take all the points and put them on the curve, right? Now, my data set is now in the two-dimensional space. It's no more on the x-axis. It's x-axis and x squared axis line, right? This is a two-dimensional plane, and I'm showing my data point like this. Can I classify this guy by a line? Can I do it? Yes, I can do it. Just draw a line. I mean, it's not a perfect drawing, but you can draw a line, right? If you play with that, the curvature of the figure, you can always do it, right? So, what's happening here? X itself is not linearly separable, right? When I'm just on the x-axis, it's not happening. But the thing that is happening is that when I go to the higher dimension, so when instead of just looking at x-axis, I look at x-axis and y-axis with y being x squared, then I get my data set represented in a form which is now linearly separable, right? So this is the whole idea of support vector machine. So what is the key idea? The key idea is that when your data set is not linearly separable in its own dimension, maybe if you just map it with one specific mapping to higher dimension, in that higher dimension you can do the linear suppression. Okay? So if you have x, in this example that we had this x, right? But this x was not linearly separable. I just took it into two-dimensional space. So every single x, instead of looking at x, I looked at x tilde. And that x tilde was basically two-dimensional point. The first entry was x itself. The second entry was x squared, right? And now, when I make my data set, when I replace in my data set instead of x's, all the corresponding x tildes, okay? If I represent my data set now in this form, Now this new data set, which instead of that one dimension is in 2 dimensions, is going to be linearly separable, right? This is the key idea. So maybe you can find this function phi that I show here. We have the example, for example, the phi exactly here. But maybe we can, in general, for any problem that we have, we can find this phi such that this phi takes our point in the dimension that it is. It just maps it to a higher dimension. And in that higher dimension, we can do linear separation. Everybody's clear? Yeah? So, that's the story. So, a nonlinear problem in lower dimension, it could be essentially get linear in higher dimensions. How high we should go? Well, we still need to talk about this. But it might be that when it's nonlinear, you go to the higher dimensions, you get linear, right? So, let's... okay. Let's just formulate what we saw here in a more general case. So in the general case, if I have a data set, and this data set has a bunch of x's, and these x's have a bunch of labels, so these x's could be, in general, in d-dimensional space. And what I can do, I can just send it to the higher dimension, right? So if I can find a very good function phi, that function, some people call it the representation function, some people call it the feature extraction function, and some people, including me, which are a very limited number of people, call it embedding function. And I call it because in NLP we also do the same thing, and we call it embedding there, okay? So any name is okay. So embedding function, what it does, it is start from one point in d-dimensional space, it takes it to the higher dimension, right? So phi of xn is larger than x in dimension than xn itself, okay? In our example, x was one-dimensional, phi was two-dimensional, right? Now, when you get into that new dimension, then the next thing that you can do, you can use one linear classifier. What is better than SVC, right? We can use SVC, is a very good linear classifier. We just decided right now. We can use that guy in order to do linear classification on the new representation of the data, right? On the features that are extended in higher dimension. Meaning that instead of working with xn itself, you just work with phi of xn, right? So phi of xn is the one which is mapped to the higher dimension, and then you compute the inner product with one weight. So now this weight is going to be in the higher dimension, right? In our example, it was two-dimensional weight, correct? And then you check the sign, right? You do know how to deal with this guy. So if I tell you what is the phi function, like the example I just showed you, cat or dog, then you can solve this problem, correct? You're going to get everything in the higher dimension. You just find the W using, for instance, SVC, right?
Well, like in the example you showed, it was a single dimension. So you have x and you have x squared.
Yes.
But if you had two-dimensional, do you just do x squared and you do y squared, and then you map a matrix E like as a 2x2?
Yeah, this is one choice that you could have. You could have like x and y, and then from this two-dimensional space, you go to the four-dimensional space. But I'm going to specify a good choice of that phi later, okay? And then you're going to see how you can do it. Okay? Yeah, no worries. Yeah. But this is possible. In general, you can come up with any, this is a very big question. What's going to be that representation phi? But at some point, I mean, deep learning helps us to get rid of that. Okay? So this is the feature classification, so that's it. And say that you just got your data set, you just went to the higher space, and then you did you solved the classification problem, you find your W, right? And now if I give you a new data point, if I give you new X, and I want you to specify the class of this X, what you're going to do, you're going to get that embedding function phi, you put X inside it, you find out what is the higher dimensional feature, and then you pass that higher dimensional feature through your linear model, and then you're going to see the sign, right? It's going to classify that one. So everybody's cool? So everything is as before. The only difference now is that we have this embedding function, which is taking the nonlinear space of data and map it, hopefully, to a linear space. Now, this example, right? how can I think of going to the higher dimension? So I have one plane, a bunch of points are green, which are in the center, a bunch of points are around it, which are red, right? Can I do it in higher dimension? Yeah, if I add a third dimension, then I can just map those red points somewhere up, and I keep the green points down, right? And then there is one plane which is now separating these two different points, right? So you can think of it in this form. So I'm going to get that green and red point inside two-dimensional space. We are still in the two-dimensional space, right? And now we add the third axis, right? And then we do the mapping size that these red points, all of them, are going to go above that one plane, and all the green points are lying below that plane, right? And then you have this three-dimensional plane, which is dividing the two classes, right? Higher dimensions, we cannot show it, but you can think of it in general. Everybody's clear? Now, this is, as I said, what we call a support vector machine. So what support vector machine is basically a support vector classifier, which is not working with the data itself, but is working with the feature extracted by the embedding function, right? And that feature is a higher dimensional thing. This is going to help you to do the nonlinear classification as well. So essentially, if you can find any good embedding function, then the problem is solved, right? So any nonlinear classification, you can still do it, right? But there are a bunch of questions coming up here. The first question is that, what is exactly that embedding function? How can I find that embedding function, right? So it's a big question, but we're going to talk about this. The second question is that, well, say that we are in two-dimensional space, or I don't know, in 10-dimensional space, and we essentially have the feeling, okay, maybe if from 10-dimensional space we go to 11-dimensional space, then this is not going to get linear, but somehow if we get from 10-dimensional space to, I don't know, 30-dimensional space, at some point we're going to get linear, right? So if we go very high in dimensions, probably we can get linear, correct? Because we have so huge hyperspace that could just divide the points. That sounds logical, but the point is that we need, in this case, to work with very, very high dimensional features, right? So instead of having vectors of dimension 10, now I need to have a vector of dimension, I don't know, 1,000. And this sounds a bit quite hard, right? Because I need to just put the function, do the transform, then I make this, compute the inner products, and then do the SVC, right? But the cool part about this is that the idea of kernel trick, we essentially see that we don't really need to work in the high dimension. We don't need to get there. We can remotely do everything in our dimension. How we can do it? So, you remember when we solved the SVC problem, we ended up with this expression, right? I called it the dual problem. I told you once you have the inner products, you can put it here in this expression. Then it's going to be a function of lambda. You solve it in terms of lambda. You find the dual optimal values, right? Lambda stars, you're going to find it. And once you find these lambda star, then you make your vector W being the average of these support vectors. And if you get any new point, you basically again need to compute the inner product of your new point with all the support vectors, right? The idea of cross-validation, correct? So essentially what we said there as cross-validation was the fact that the only thing we need is those cross-correlation, those inner products, right? As long as I have the inner product, I can do both training and inference, right? Everybody's cool? Okay, now let's do this for SVM, right? If I get my mapped features, if I get my new features, that phi function, okay? And I use it, I put it inside the SVC solution, what do I see? I get my embedded features, which are those phi versions, and now these phi's are the one which are representing my data points, right? So in the dual function, instead of inner product of my x's, I'm going to have the inner product of their embedded one, right? Phi of x, correct? This is the new data point, right? The higher dimension. So again, I just need their inner product, correct? Now, this is one thing. Now, if I have the inner product, I can solve this problem. And once I solve this problem, again, I do have W star, but essentially, I don't need to really compute W star directly. Oh, here there should be a phi. Sorry, there is a typo. So in the left-hand side, in this summation, please add this phi. This is going to be phi of xn. I just copy-pasted, did a mistake here. The second line, W star, is that summation, lambda star, Vn, phi of xn, right? So now, but I don't really need to compute that W star. The only thing that I need to do is to just compute the phi of my x, the inner product of phi of my x, with phi of my support vectors, right? Now, what is happening here again is that, again, we only need cross-validation, but the cross-validation of the embedded features, right? So I don't really need to know phi itself, and I don't really need to compute phi itself as long as I do know what is the inner product of phi at any two different points, right? Correct? This is what we call it the kernel. Okay? So the moral of the story from this argument here is that I don't really need to know the phi vector, phi function, which is potentially getting my data from very small dimension and takes it to a very huge dimension. I don't need to know that phi. The only thing that I need to know is the inner product of phi with itself at two different points, right? So as long as I know how the embeddings are correlated, then I am fine. I can solve the SVC problem for this new feature space, right? And then this is what we call it the kernel, right? So the kernel is essentially the inner product of phi at two different points. So kernel at point xm and xn, in general, is a function which takes two different points as input, and at the output is going to give you the correlation between two different points if you have used phi function. But if now I remove this phi function, I don't tell you what is phi, I simply give you k, the kernel function. Can you still solve the SVC problem for this new high-dimensional problem? You can do it, right? You just replace k in the place of every single cross-correlation, right? And then you can solve the problem. This is what we call it the kernel trick. The kernel trick says that it's true that somewhere, in the very behind the scene, your data is going into the high dimension, and then based on that, you conclude what is the label. But you don't really need to do this mapping. As long as you do know what is the kernel, you can just live in this, finite dimensional world. Clear? Everybody's clear? Any questions? Okay, so the only thing that we need is the kernel function. We really don't need the embedding function itself. Phi, I don't need it, as long as I know what is the kernel, right? Now, if I replace that kernel here, what is going to happen? If I replace the kernel here, now I need it here to have, phi transpose times phi. No, I just replace it with the kernel function, right? So I do know the kernel function. I put xm and xn inside that. Then I get the cross correlation, right? So I don't need to know phi. And now if I want to do the new, again, I have the typo, so there it should be phi. But that left-hand side expression is not really important. If I want to do the invariance, basically I need to just get my kernel function. I put my new point and all the support vectors. And then finally, I just sum it up to find out what is the label of this new x, right? Everybody's clear? Any questions? Doesn't that sound like magic? Like, are you excited? You can share your excitement with me. I was excited the first time I read this, okay? So, it's no surprise. Ooh, that's really genius. And to be fair, I mean, it took decades for the people develop this idea. So it took decades for people developing this idea, VC guys, to end up with this solution, actually. Because I mean, it's now obvious when I explain it, but you say that the question is simple when you know the solution, right? So they didn't know the solution, so it took them. So the idea of maximizing the margin was somehow in 60s, but they came up with this final SVM in 90s. So it took them quite some time to get into that idea. Makes sense. Mm-hmm. So, okay, so moral of the story, SVM is basically your SVC, and this is using, embedding, but you essentially don't need your embedding, you just need to know the kernel. As long as you know the kernel, then you're fine, right? And what you can think of is that actually maybe it's better that we say SVC is SVM when we set the kernel simply to be the inner product, right? But you can come up with any kernel, right? A very weird kernel, and that weird kernel could be better than inner product, right? Okay, so that's the story now. Let's have a bit of visualization. So this was the nonlinear problem that we had. And initially, when we were thinking of embedding, I told you that we need to go higher dimension, right? So I take the green points somehow higher in altitude, and I keep the red points inside, and then I just draw that plane, right? This was the solution, thinking in terms of embedding, but actually you don't really need to do that, right? The thing that you're going to do the same thing as SVC again. So you start from the, say, first point, and you are going to just check its cross-correlation with every single other point inside data set, but this time you don't simply compute the inner product, we use your kernel function, right? So you use your kernel function, you put the first green point inside that, the red point inside that, you compute its correlation, right? And you do it for every single body inside this data set, right? So you start from the first pair and you just check all the possible pairs, right? And once you have done this, now you have all the things you need to find to solve the dual problem, right? Once you solve the dual problem, you know what is the support vectors, right? Because those data points whose corresponding dual variable is non-zero are supposed to be the support vectors, right? So when you do it, maybe you end up with these guys being the support vectors, right? And now if I give you a new data point, this new blue point, the thing that you are going to do is that you simply check the you do the cross-validation of this blue guy with all of the support vectors. But when you want to do cross-validation, what do you use? What is it? Kernel, exactly. So you are going to use the kernel, right? So kernel value for these 2 points, kernel value for these two, and then you just write that linear summation, and then you're going to know what is the sign. Okay? Everybody's clear? So this is the idea of support vector machine, and now we get into the other question. So the other question that we have is, okay, that sounds fine, so we don't need to know really embedding function, but at the end of the day we need to know kernel, right? And what kind of kernel we should set, right? This is a very hard question, so you cannot come up with a conclusion. Like this kernel, just put it and it's over, right? You try different kernels, right? A bunch of things people have came up with. So one of them was the polynomial kernel based on the intuitive illustration I had in the primary example. So in the primary example, we saw that we get x and we put it in the 2-dimensional like x squared, then it's going to work fine, right? And people said maybe if we go with a high-dimensional polynomial, we always go for better, right? But again, you just need the kernel. You don't need the embedding, right? So how do they do that? They define the polynomial kernel to be of this form. So you get 2 points if I give you 2 different points, xn and xm. You just compute the inner product of them. You add it with a constant. You take it to power p, right? This is a polynomial kernel of order p. And you might say, how it is connected to the other thing we talked about? Let's try it for one particular case. So let's say that c value, the constant here, first of all, assume that all of x's are 1-dimensional. So we're not doing 2-dimensional, okay? 1-dimensional. Clear? Now, xn and xm, both of them are 1-dimensional, so I can write it down simply as xn times xm, correct? Now, say that constant value c is 1. So it's going to be 1 plus this guy to power p, and let's do it for order 2, okay? 2. Then, how can I open this term? It's going to be, okay, let me do it right here. So it's going to be 1 squared is 1. This guy squared is every single guy squared. 2 times this guy, right? So it's going to be this guy, so I don't need the brackets anymore. Xn squared, xm squared, and then I have plus 2 xn xm, right? Correct? Okay. Now, I can write it down in this form, and you tell me whether I'm right or wrong. So I'm going to take xn squared, put it at the first entry. Here, I am writing down this 2 to be a square root of 2 times the square root of 2, right? And then I replace xm here, this guy, multiplied by a square root of 2 xm, correct? It's the same thing, right? Now, I'm going to write down the next entry here, a square root of 2 times xn, and the last guy to be 1. Okay, this is one vector, correct? And I compute its inner product with this one. So it's going to be xm squared, the square root of 2 xm, and 1. So if I do this inner product, do I end up with the same expression? Xn squared times xm squared is going to be the second term. A square root of 2x and a square root of 2xm multiplied is going to be the last term. 1 times 1 going to be the first term, right? Correct? So when I compute this kernel, it's essentially like I get my x and take it to the higher dimension, which is I get x itself, and it's a square, right? And I put them as the features, right? And you can imagine simply that when p goes for higher values, it's like you're adding more expression to yours. So if p is 3, then you have a feature vector which is going to be your x point cubic, your x point squared, your x point itself, and maybe a constant, right? If you go higher, then this vector is going to be larger and larger. But essentially, you don't need to compute those very long vectors at all. You just need to compute that kernel function, which is still in your data domain, right? Because xn and xm, both of them are in your data domain, right? Data space. So this is one solution. So this is basically what I did you on the board. So you can write it down. You open up the term. You can show that this is the inner product of these two. And you can essentially think that your embedding is of this form, right? But if you increase p, it is going to be larger. Eh? And if you have, I think one of your friends asked when we have a multidimensional vector, then again you can put it inside this expression. You see it's going to open up, right, into different. Then you can just find out what is the embedding function. By the end of the day, you don't really need the embedding function, right? You just need the kernel. The kernel is going to solve everything for you. Yeah.
As opposed to being 2D, 10D, like how do you...
I mean, here you don't really need to know what is the target dimension, right? Because you don't specify the embedding. You specify the kernel, right? So in this example, I could show that this is equivalent to thinking of this, target dimension. But you don't really need to do that. And you're going to see it in the next example. In the Gaussian case, essentially what we are doing, the kernel is taking us to the infinite dimensional space. Okay? So you don't need, because you don't want to work in that space, correct? You just need the kernel, and kernel you can always compute it in your own dimension, right? For instance, in this case, I mean the inner product that you do to put inside the kernel is in your own space, right? D-dimensional.
Yeah.
And then you don't really care about what is the target dimension. I mean, you can go potentially to very huge space, right? Yeah. So any questions? Everybody's cool? Great. So one other choice of kernel is what we call it the Gaussian kernel. And the Gaussian kernel is simply the exponential function. So if I give you two different points, you just compute the difference between these points. Then you compute this Gaussian function. So take it to the exponent. Why I have so much typo today. So that squared should be after that form. Of course, I mean, it doesn't make sense, x and squared. So this is a typo here again, sorry. So out of the form. And then you divide it by some sigma, right? So this is the expression for the Gaussian kernel. So some people call it radial kernel. Radial basis function kernel, RBFK. Okay, so not JFK in the States, RBFK, right? RBFK you see a lot in the data analysis work. So many people use this kernel. Okay? So now, one thing that we can think of this guy is essentially that this guy, when you want to do the same thing as I did on the board for the polynomial case, this one. So if you want to do the same thing, you can see at the very end, this is essentially the same thing as you get your x, you take it to the infinite dimensional space, and then you compute its inner product with itself, right? So your phi, your embedding function, is taking your point from one-dimensional space, it takes it to the infinite dimensional space. Okay? And how you can show it, so this is the idea here, your kernel is essentially taking, the embedding is taking your point into the infinite dimensional space. I'm not sure if you see it immediately, but you can try it at home, okay? And if you want to try it, just use the Taylor expansion, right? If you have your exponential function, e to power x, you can write down the Taylor expansion, which is going to be, exponential function, the derivative is always itself, right? To any order. So it's going to be summation of an infinite dimensional polynomial, right? And then you can see that basically you have these two polynomials with those particular weights that you have in the Taylor expansion getting multiplied to each other, right? But you don't need to go to the infinite space, right? You're basically still in your space, your own data domain, but the kernel is taking care of it. Okay, so any question on that? Everybody's cool? Okay, now, one other thing that you might ask me is that, okay, it's nice, we're working with the kernel, you showed us a bunch of, famous kernels that we use in practice, but what is the best kernel, or how we can find the good kernel given that we have a problem? So the answer to this is that nobody knows what is that, right? You cannot say, you can try it, but maybe it doesn't work, right? Even the Gaussian kernel, there's no guarantee that it works, because it's true that it's taking everything to the infinite dimension, but it's doing it with specific weights, right? So you are not specifying anything there. You just put the kernel, and then that mapping is being done by itself, right? Correct? So when I fix my kernel, if I tell you this is the kernel function, then essentially you have no control on the high dimensional space. You're getting rid of the issue working with high dimensional space, but you don't have access or control on that. So it might be true that, going to higher dimension is going to help you, but the point is that it could be the case that that kernel is when it's taking you to the higher dimension, it's essentially not again making your problem linearly separable, right? So if in the three-dimensional case, like if, for example, in the one-dimensional case, I get my points from one axis and put it again on a line, still it's not going to be linearly separable, right? So if I tell you to use a linear kernel, then it's still not linearly separable, right? If I do a kind of weird function again, sigmoid function or whatever, again, it could be the case that it's not linearly separable. So if you come up with one fixed kernel, it's essentially that you have fixed your embedding, and there is no guarantee for the problem that you have, this embedding is going to transform your problem into a linearly separable problem. You just hope for that, right? You just use that kernel. You hope that after doing the kernel trick, you are ending up with a linearly separable problem. So this is what we call it feature engineering. When you are specifying the kernel, you are engineering the features that in the higher dimension, right? So you are not learning anything here. You got your data. You have a fixed function taking it into the higher dimension, right? So you came up with one engineering solution. I know that polynomial is good because I'm the engineer, so I'm going to put it there, and I do the problem, right? But it might be that it doesn't work, right? It might be that given the data set you have, is not working, right? So the feature engineering is not the best thing you can do in practice, but for many problems, for a long time, it kept working, right? With, for example, the Gaussian kernel, you were going essentially into a very, very high dimension, that engineering was somehow hiding behind the huge dimension. At the end of the day, for some problems, we get into this trouble. This Gaussian kernel was not perfect. So what is the better solution to that? If I don't want to engineer the features, meaning that I don't want my embeddings to be fixed or my kernel to be fixed, what is the better solution? Anyone has a suggestion? I'm waiting for a suggestion. How can you just replace engineered kernel with something better that is adaptable to your data? Great. So you can set your kernel again to be something that you can learn its parameters, right? This is what Vapnik used to say in his own original paper. He said, let data speak by itself. So why should I specify the kernel if I can just set the kernel to be a kind of parameterized function? And then when I'm doing the training, instead of just finding the W, I also find the parameters of that kernel, right? So this was the idea of representation learning. So you learn the kernel. You find out what is the right kernel given the data set that you have. Meaning that you have one kernel, maybe you come up with one expression, and that expression is essentially depending on a bunch of parameters, theta, for instance, right? And then when you do the SVM, at the end of the day, that thing you end up with is depending on that theta as well, right? And when you want to find the right kernel, you just try to minimize your empirical risk, not only with respect to W, what we did in SVC, with respect to W and theta together, right? So I am going to learn the kernel from the data itself. This is a better idea because given the data I have, I just adapt my kernel to that data, right? Okay? Everybody's clear on that? So this is the idea that we call it representation learning. This means that it's true that we are not explicitly computing or finding the embedding, but we are somehow indirectly finding the right embedding by learning the kernel itself, right? So when you learn the kernel, each kernel is corresponding to one huge dimensional, representation. And what you're essentially doing is that you're learning that embedding or that kernel, right? So people used to call it representation learning, or some people used to call it kernel learning, okay? Now, for instance, one simple example. So you saw in the Gaussian case here, we had that sigma value, right? So how do you set that sigma value? You don't know, right? So maybe you can leave it as a parameter, and when you are doing the training, you try to minimize also your empirical risk with respect to sigma, right? And then in that sense, you're just learning one parameter inside your kernel. So this is one simple example. You can essentially think of more complicated cases, right? Any questions? So everybody is clear on representation learning? So the idea of representation learning is nothing weird. So basically you have SVM. The only difference is that you are not fixing kernel anymore. You're essentially just learning the kernel also together with your classifier.
How complicated is it?
It could be very complicated, but deep learning is going to resolve the whole issue. Yeah, because essentially what you do in deep learning, you have all of these layers, and then in neural network, and you end up with the last layer, right? That is the linear classifier. That's the SVM part, right? And everything behind is just simply learning that embedding for you. So people, through time, those who were working on neural networks, they saw that this is very capable of expressing different functions. And when people start to see this representation learning, they said, like, okay, those guys seem to be a good thing. This is the point when those ideas just got merged. Because essentially, if you want to just make one very good kernel, it's better that you replace your embedding with a neural network. Then that is going to do it for you. So, any questions? Great. So, moral of the story, the representation learning tries to just do the learning of the kernel together with finding the classifier for you. And then there had been time that people were doing kernel learning, representation learning. Bernhard Scholkopf, if you know him, he is in ETH Zurich. He is a quite well-known person on kernel learning. He did a great job, right? So I think, if I'm not wrong, he was working with Vapnik. So he spent lots of his graduate study on kernel learning. But eventually, many people, when they started to do the deep learning, they started to see that, when the deep learning got to be a thing, people started to see that, well, we don't really need to go for very weird kernels. Maybe we can replace all of this kernel thing with a neural network, right? And that neural network is going to do the job for us. So we don't really need to think of a weird function with lots of parameters there, which is still good in many problems. So still people do representation learning. Still people do kernel learning in some specific problem, and that could work better than deep learning, as I said, in some specific problem. But if you think of a general problem, then maybe it's a better idea. You get a linear model, you just repeat it a couple of times, then you just connect it to a bunch of new linear models, and so on. And this is going to make you what we call it nowadays neural network, right? So that is a neural network. So everything behind the scene for understanding the kernel could be done by a neural network, right? So that was the point. that people said like deep neural network could make very great kernels for us. And then maybe instead of searching in general kernel space, maybe we can focus on the deep neural networks, okay? Now, this is why people say that deep learning is a subset of representation learning, right? Because deep neural networks are a very specific form of representing your data, right? Which is a very rich form, very strong form. You pretty much can do whatever you want because neural networks are very expressive, right? But representation learning by itself is a more general thing because you don't necessarily need to have your representation being shown by deep neural network, right? You can learn directly the kernel. And your kernel could be a weird thing, right? And representation learning itself is a subset of machine learning, right? Because not all the time you're doing SVM with a kernel, right? You can come up with another solution, right? So deep learning is a subset of representation learning is a subset of machine learning. And I hope this is now clear for everybody, okay? So deep neural networks somehow made the bypass for us, and nowadays we don't get deep into the kernel learning, even though, as I said, it doesn't mean that the area is dead. I mean, there is still lots of things being done by kernel learning, okay? So you might end up with a problem where doing the kernel or representation learning directly is going to be better than, I mean, even nowadays, we are still having problems which are getting solved by kernel trick much more efficiently. So you might take a look at this, but in this course, we're now going to just migrate into neural network world. And then we basically try to first understand why neural networks are cool things, because they are very expressive. They can do whatever we want if we are large enough. And then out of that, we just get into a bit of flavor of what deep learning is, okay? So this is what going to be the rest of this course. So this is, where you can check SVM in those textbooks if you're interested. After the next week is reading week, right? And then you don't have the lecture the week after, as I said at the beginning. So you're going to have your practice questions. You can practice during your time. And then on the next tutorial, which is the week after reading week, you're going to have them solved by the TA. And then on second next Tuesday, here we are going to have the final, midterm exam. And it's going to be super easy. So I don't have any issue with anyone. So I don't try to make it hard, trust me. So when you study, don't need to think of me as an evil. So I basically try to make it as basic as the assignments you had, okay? So see you on second next Tuesday.